All right. Probability. So, we were looking at some prior to the break concepts of statistics and statistical studies, and ways of collecting data, and then ways of organizing that data, and then being able to make draw some conclusions from the data that we collect. Probability ties in with statistics, is particularly looking at distributions. And we're not going to get to that aspect of it. That will be reserved for a statistics course. But we're going to kind of just start with a basic study of what is probability. So I think you're all familiar with probability in terms of, lotteries, Powerball or Mega Millions, and that you have better odds of what being struck by lightning than what winning the lottery. And one out of some odd millions. So we're going to maybe keep it a little bit simpler than that. So let's, as an example, just kind of get a hold of a couple concepts in dealing with basic probability. The idea of outcomes and events, and the difference between the two. So let's singular event outcome. All right, so let's say we have two coins, right, heads and tails, and we flip each coin and look at what the results are there. Now, we could flip the coin, and I'm going to abbreviate with T's, and each of them are tails. Now, if I was really wanting to know how many heads could I receive, that was actually what I'm interested in, then there would be 0 heads if each coin flipped up tails. Now, I could flip this thing first coin tails, second coin head, but the event would just be what, 1 head. And if I went here and first flipped head then tails, and again, I'm interested in how many heads can I get out of 2 coins, 2 flips, and then that event would also be ultimately just 1 head. Now, if I flipped each of them head, then 2 heads. Okay. Now, so in this situation, just flipping 2 coins, there are 4 possible outcomes, but 3 events. And because these two, there's no differentiation. Tail heads, if I'm interested in just knowing how many heads can I get out of flipping 2 coins. So 3 different events there, 4 different outcomes. Right? So outcomes are the most basic possible results of observations or experiments okay, and that is it. An event consists one or more, let's put more, there, no one, of one or more outcomes that share a property of interest. Okay. So that, again, going back to our simple example here, each one of these are the most basic possibilities we could get flipping two coins. If what I was interested in, how many heads did I get on two flips? Again, here there's one outcome, and that was the event, no heads. But here in each one of these, two outcomes, it would just really still comprise just one event, and that is obtaining a head. Okay, so now if I take a coin and I flip it, and I assume it's fair, meaning it's not weighted in any way, and it's what equally likely that it lands heads or it lands tails. You may hear the phrase it's 50-50. Meaning if I flip the coin 100 times, it's going to come up 50 heads, 50 tails. But in terms of expressing probability, so one coin flip as an example, notationally, I'd write this probability. So this stands for probability of flipping a head, one flip. Then there would be what? One way I could get it out of what? Two possibilities. Okay. So, or another way to think of it is the number of ways this could occur, which there's only one way out of the total number of outcomes, which is two. If I flip a coin, two possible outcomes, heads or tails. And so I can express it as a fraction. Of course, I could put that in decimal form, which would be 0.5. As a percentage, that's what, 50%. About a 50% chance, right? So so if I'm looking at method of calculating equally likely outcomes, so method of I think I want the word for here. I'm sorry. For equally likely outcomes. One, count the total number of possible outcomes. Two, this is where we'll differentiate outcomes and events. Among all the possible outcomes, count the number of ways the event of interest that you're interested in. Say we were wanting to know, flip 2 coins. How many, how can I get a head? Flip, get at least 1 head. All right, so count the number of ways the event of interest, and we'll call that event A, can occur. So going back to our flipping 2 coins, looking at how I could get ahead. There were 4 possible outcomes, but 3 events out of that. One event that I get no heads, one event I get 1 head, and one event that I get 2 heads. There were 2 outcomes that each comprised 1 event of getting 1 head. Right. So from there, step 3 is actually determine the probability. It's not probability. Try to spell that again. Probability. Determine the probability. So notated this way: probability of the event A occurring. And that is probability that A occurs is, as a fraction, the number of ways that event can occur divided by the total number of outcomes. So if I go back to flip back real quick to here, and I would say, A, the event of obtaining 1 head. Okay, so that probability here, look at it here, there are 4 possible outcomes. But out of those outcomes, there are 2 ways I could obtain a head, either first flip a tail, then a head, or first flip a head, then a tail. So, which could reduce down to 1/2 or 0.5. If I said, what is the probability of obtaining 2 heads? It would be 0.25. I'm not writing it down. But because it would there is only 1 way I can get 2 heads. That is right here. But there are, again, 4 possible outcomes there. All right. So, any questions so far? Okay. So let's look at calculating some other probabilities. We all have this one here, this page.
Yeah, I'm okay.
All right. Okay, so let's say I wanted to calculate probability of getting a 3, rolling a 6-sided dice or die. So notationally, probability of rolling a 3. Now, number of ways of getting a 3 is 1. There's one possible outcome. You roll, you've got 6-sided dice. Only one side of that 6-sided cube has a 3 on it. So, so that is the number, writing it down in words, the number of ways the outcome of 3 can occur, which again we know is going to be 1, and the total number of possible outcomes. So there is, again, just one way a 3 would occur, but there are 6 possible outcomes. So it's going to be 1/6, which again, you could put in decimal form, or you could just leave it as 1/6. All right. Again, we're assuming the die is fair. That is, it's equally weighted to each side. So there's not a possibility that it rolls just to one side, which again would not be a fair die. All right, look at another example. So playing cards. Right. So this time I got a standard 52 card deck. So there are 4 suits. Each suit, so you've got hearts, clubs, spades, and diamonds. Each suit has 13 cards. So usually, count them up ace through 9, or ace through 10. Then you've got the jack, king, and queen. But it's 13. So if I said, what is the probability that I do a shuffle of the deck, so they are randomly shuffled, what is the probability of drawing a spade? Right. So the total number of outcomes or spades is 13. There's 13 spades in a deck. There are 52 total cards in the deck. Now 13 out of 52 will reduce to 1/4. So,
and will it ask for a decimal form, or would you like us to
it
leave
would
like that?
specify in the homework.
Okay.
Yeah, it'll specify. So if it does, and it'll tell you how many decimal places. But in
Okay.
this case, it terminates, 1/4 is 0.25. Now, like the 1/6, I think that's repeating. I think it's 1/6 is 0.1 and then 6 repeating. So, and we typically don't write that down as the probability. What we would normally do is, if we were going to say, take it to hundreds place, or 2 decimal places, I would end up rounding to 0.17. So, but it'll specify in the homework.
Okay.
Right. Okay. So let's do this. Another example. Now, where we were not going today, but just to give you a preview, as I'm going to mention a few things on Thursday to follow up today, especially like dealing with cards, what is the probability that I draw a spade and then draw again from that deck randomly and draw another spade? And how would you calculate that probability? And it will turn out that we would use multiplication. But and that is, we would have two events. What is the probability that I first draw a spade, as we did right here? But then ultimately what I want to know, what is the total probability that on the second draw, I also draw a spade? All right. So again, you won't have a problem like this, but this is where you would head. And so when you were thinking about doing that probability, you would first calculate what's the probability I draw a spade on the first draw randomly. And it's, as we calculated, 0.25 or 1/4. But on that second draw, what you have to remember is you've already drawn a card. So you're no longer drawing from 51 or 52 cards. You're now drawing from 51 cards. And there's not 13 possibilities. There's only 12 because there would only be 12 spades left. If I said, what's the probability that you first draw a spade, then a heart, you would take the first, probability of drawing that spade, which is 13 out of 52, 1/4. And the second draw would be 13. If I said, now you draw a heart, would be 13 out of 51. And then you multiply the two fractions together. And that's going to be your ultimate probability of in sequence drawing a spade and drawing a heart. All right. So that's kind of where things head. All right. Let's do another example, not dealing with cards. So what is the probability? This is going to be a family one. That a randomly selected family with 3 children has 2 girls and 1 boy. And assume boys and girls are equally likely. So that is, you just go out and pick any family that has 3 kids. All right. So what is the probability that any randomly selected children or family, any randomly selected family that has 3 children? So caveat that all the families you randomly pick from have 3 children, but you don't know what the gender is. So you randomly pick a family, 3 children. What is the probability that out of that family you pick has 2 girls and 1 boy? All right, so then figuring this up. Now remember, there are 3 kids. So what, and we're going to go with birth orders here. First kid, second kid, third kid. So even if they're triplets, they still come out in a particular order. So what are all the possibilities here? Now, a couple ways we could figure it out. We're going to write down, I'm just going to write down all the possible outcomes first. It could have went what? Boy, boy, boy. Could have been, okay, first is boy, second one was a boy, third one was a girl. Could it be boy, girl, boy? Could be boy, girl, girl. Could have been girl, and then second and third were boys. Could have gone girl, boy, girl. Could have been girl, second girl, third boy. Or girl, girl, girl. Now count them up. They're 1, 2, 3, 4, 5, 6, 7, 8. All right. And that's it. Just 8 different ways. Now, if you didn't want to write every single possibility down like this, you could think of it this way, that for each birth, first birth, then the second birth, the third birth, first birth, have child, then if it was equally likely that the birth was either a boy or girl, then you would be looking at two possible outcomes. And, on the first birth, it would be probability of getting a girl would be 1 out of 2. But the second one, there would be two possible outcomes. And the third, there would be two possible outcomes either. And then if you just went 2 times 2 times 2, that is 8. So now, so 8 possible outcomes. Now, what we're looking at, again, out of these 8 possible outcomes, and we're wanting to know the probability that any randomly selected family with 3 kids, they have what? 2 girls and 1 boy. 2 girls and 1 boy. That is, there are 3 possible outcomes here for that one event, that I randomly select a family that has 2 girls and 1 boy. So the probability that I randomly select a family here that has 2 girls or 3 children, and that 2 of them are girls and 1 of them is a boy, that probability is going to be 3 out of 8, which again, decimal form does terminate 3.75, 37.5%, 37.5%. Okay. All righty. Let's do another example. Let's say this time I'm with a large group of people, and I randomly select one person attending in this big, huge group. Let's say it's a group of 200 people in a room. And I randomly select one person. What is the probability that that person was born on July? Right? What is the probability of, just large group of people? I don't know how many people. I just threw out a number, 200. It could be 300 people in the room. But I randomly select one person out of that group. What is the probability that they have a July birthday? All right, so every possible birthday represents an outcome. So there are 365 possible birthdays. So that's your total number of outcomes. Now, July has 31 days. So it would have to be 31 out of all the possible outcomes, which was 365. So there were 31 outcomes for that one event being that they had a July birthday out of all the possible outcomes, which was 365. Now, here, this one doesn't terminate easily, but rounding to 4 decimal places is 0.0849, which is a little bit more than 1/12. Okay. So now another way to approximate a probability is to approximate probability of an event A by making observations and counting the number of times that an event A occurs. Now, this approach is called a relative frequency, which is a term we've dealt with before, method, or sometimes called an empirical method. So for an example, if we observe that it rains on an average of 100 days per year, we might say that the probability of any randomly selected day that it rains is 100 out of 365. So relative frequency method, or again, sometimes is referred to as the empirical method. Two steps. One, you either by experiment repeat or just observing a process many times and count the number of ways or times the event of interest occurs. Call that event A, general, occurs. Right. And then again, two, we're estimating this. Estimate the probability of that event occurring. Which again, the way I want to say is the number of times in your observations A occurred over your total number of observations. So and this one is kind of next example is kind of applicable to us. I think I could put it right in here. Flooding. We live on a river, so it's not like it used to be, but you know, in my lifetime here, we've had several substantial floods. But then you'll hear, you know, really big floods every what we call a 100-year event or a 500-year flood, so on and so forth. So if you look back and say you were doing a thing on a 500-year flood, and geological records indicated that the river has crested above a particular flood level 4 times in 2,000 years, then I could use this relative frequency method or this empirical method to estimate the probability that the river will crest above flood stage and that flood level in the next year. You would just do the probability in this case of that event occurring, that you were going to flood or be above the flood level, as 4 out of 2,000, which would be 1 out of 500. Okay. And since you're averaging 1 time out of 500, that's where you get the term 500-year flood. Okay. So now, Um, do another example here. Let's do a fair coin test. All right. So is this coin balanced? Is it fair? So, well, actually two coins here in this problem. So let's say we toss two coins 100 times. So 2 coins, flip 2. And 2 coins, and we're going to flip 100 times. So 100 times I will flip each of the 2 coins. You even flip them simultaneously. Now, we looked at all, there what, 4 possible outcomes. If I just flip one time, right? There was, flip, get 2 tails, flip, get a head and a tail, flip, get a tail and a head. And then the last possibility is head, head. So we're going to flip them 100 times. And let's say we flipped and I came up with, at 100 times, 0 heads. Occurred 22 times. 1 head, flipping 2 coins, occurs 51 times. And 2 heads occurs 27 times. Okay. So now, if I were to look at the relative frequency, here, I would be looking at 22 out of 100, which is 0.22. Here, I'm going to be looking at 51 out of 100, and that's 0.51. And this would be 27 out of 100, and that's going to be then 0.27. All right. Now, question. If I compare these, do I have reason to suspect that somehow these coins are unfair? Remember, supposed they're equally balanced. I got an equal probability of either obtaining a head or a tail. Now, so if I compare these relative frequency probabilities to the theoretical probabilities, and so what I mean is that goes back. So this again is this is the relative frequency probabilities. We actually wrote them 100 times. This is the data we came up with. So flipping back, I'm going to flip the pages back real quick. It's actually on the first page. Like here, I actually calculated the probability of obtaining 1 head flipping 2 coins, and it was what, 50%. So, and that's what we call the theoretical probabilities. So those 3 theoretical probabilities, the probability of 0 heads was again 1 out of 4, or 0.25. The probability of obtaining 1 head, theoretically, was 2 out of 4. There were actually 2 outcomes where I could get 1 head. And so that's 0.5. And the probability of obtaining, rolling 2 coins, theoretically, and getting 2 heads, there was only one way to do that. So it's also 0.25. So if I compare, okay, I rolled again 100 times, and 27 times I came up with 2 heads. And so the empirical probability was 0.27. The theoretical probability was 0.25. Probability of getting 1 head out of 100 rolls. And I wrote, when I did this experiment, rolling out 100 times, I came up with 0.51. Theoretically, it's 0.5. And again, 0.22 and 0.25. So when I compare the theoretical with the empirical, they're close. So no, I don't, I would not have reason to suspect that these coins are not fair. And if you did this over, and this is where you can come up with probability distributions, you could then do it again 100 times. The numbers are going to vary a little bit, but you're going to be still in this ballpark is really the point. And I could do, I could do this repeated 1,000 times and I would still stay in this ballpark every single time. So, all right. So now, so basically we've come up with two approaches to finding probability. There is the theoretical probability, which again, as an example, we have right here, or the empirical, where we actually do an experiment. So theoretical probability, such as what we have right here, is based on the assumption that all outcomes are equally likely and is calculated by, again, dividing the number of ways an event can occur by the total number of possible outcomes. Relative frequency probability, or again, I like to use the term empirical probability. That's where we base on observations or experiments, such as what we did flipping the two coins 100 times right here. There is a third, and it's called subjective probability. Now, subjective, the term subjective right immediately means it's not exactly scientific. We may even use the word intuition. So you calculate or estimate a probability based on just your experience or intuition, and that's all. So, just based on my experience, I may conclude that excuse me, within a given ski season, we're going to get 3 to 4 snowstorms within any 3-month period. That's just kind of my when I call not a set of flurries or a little dusting, I'm actually talking about a major snowstorm. So within a ski season, in my experience and all the years I've skied, maybe you get 3 a season. So anyhow, and that would be an example of subjective probability. It's not really, I'm not actually doing any serious observation there. I'm just kind of ballparking it based on my years of experience skiing. So if I want to look at a couple of other examples here and just classify as either going to be theoretical, relative frequency, again, remember is empirical, or subjective. So if you hear, somebody selling a car and they say, I'm certain you're going to be happy with this car. Yeah, that's subjective. Maybe you will, maybe you won't. Another example, based on housing data, the chance that someone will move to a new residence during the coming year is 1 in 8. This is going to be relative frequency or empirical, because I'm basing this on data showing that about 1/8 of the population moves to a new residence in a given year. I'm looking at data that already exists. Right? And then if I have a 12-sided die, and what's the probability of rolling a 7 with a 12-sided die, and say the probability is 1/12, this is what I call theoretical, because it's based on assumption of a fair 12-sided die equally likely to land on any of the 12 sides. Okay. Now, if you here want to know the probability of an event not occurring, And then the probability, and I guess it also should be pointed out when I look at probabilities. Notice if I add up all these, I'm going to add up to 1, numero uno, or 100%, your total. So if you say the probability of an event A not occurring, then if you know the probability of A, it's going to be 1 minus the probability that A does occur. Probability of not A plus the probability of A will exactly equal 1 every time. Okay. All right. And if you write out a probability distribution and say you could even graph it, say like I wanted the probability distribution for tossing, say 3 coins. And obtaining out of that how many heads I'm going to get out of tossing 3 coins, then you would either have as your possible outcomes, getting no heads, getting 1 head, getting 2 heads, or getting 3 heads. And there would be 8 possible outcomes. Kind of, and it's noticed mathematically, it's exactly the same as the problem of having 3 kids. And saying, okay, what is the probability that 2 of them are girls and 1 is a boy? There were actually 3 different outcomes for that one event, and it was 3 out of 8. So, but if you just do a whole distribution, then wrote down all the possible outcomes of flipping 3 coins. It could be head, head, head. Head, head, tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, and tail, tail, tail. And those are all the 8 possible outcomes. Now, out of this, if I said, well, you flip 3 coins, what's the probability of obtaining 3 heads? So 3 heads would be probability of getting 3 heads out of the 3 flips would be 1/8. Probability of having 2 heads, which means one of them was tails, they're just like the 2 boys and a girl situation. There were actually 3 ways that could happen. So if I look, I could go in here and figure them out. There's 1, there's 2, and there's 3. So it's 3/8. Probability of having just 1 head, which means there's 2 tails. There's 3 of those, and no heads. There is 1 out of 8. And that's here. Now, we could go ahead and get, again, the decimal calculating 1 out of 8 and 3 out of 8. 3 out of 8 was 0.375. 1 out of 8 should be 1.25. 0.125. This was 0.375, and this was 0.375, and this was 0.125. Then we could go back and do a little graphing, which I kind of run out of room here. But say do a histogram to show that probability distribution. So I'm going to just try to do a facsimile here. Number of heads, 0, 1, 2, and 3, and then up the vertical we could go 0, Put say 0.25 and then put 0.5 and then 0.75 and then finally 1. Then we can put in our bars. So 0 is 0.125, which would actually be about right there. 1 was 0.375, which would be about right there roughly. 2 was also the same. 1 was there. So up here, I could write probability. And here again, number of ways to obtain heads, but I can draw out again a graph, a histogram of that probability distribution. Notice it has a normal distribution, normal curve. So connecting back to when we were looking at distributions and statistics and looking at what we call the normal curve. If I would look at rolling 2 dice and then summing up what the sum possibilities are, then such as I roll 2 dice, what's the probability that I get a sum of 2? Now, the only way to do that is each dice rolls up what? 1 and 1. 1 plus 1 is 2. And what is the total if I or I guess another way to say this is, what is, I roll 2 dice, what is, and one of them comes up 1. And so let's do it that way. So I roll 2 die, 2 6-sided dice, and one of them comes up as a 1. Then there are, for that one dice that comes up 1, there are actually 6 possible outcomes. I rolled a 1 1, I rolled a 1 2, I rolled a 1 then a 3, I rolled a 1 then a 4. And then I could do that for 2. I roll 1 dice of 2, and then there on that second dice there's 6 different ways that could happen. So, and I do that for all, the next one would be 3, and then all the possible rolls off that second dice. And what we come up with there at the end of the day, since there would be 6 for each and there are 6 sides of the dice, there's 36 possible outcomes on those sums. So but the probability that I roll 2 dice and I get a sum of 2, there's only one of those 36 possible ways that could happen. So your probability is 1 out of 36. Now, the event that I roll 2 dice and get a sum of 3 could happen 2 ways. I get a 1, then a 2, or I roll a 2, then a 1. So 2 out of 36. The possibility that I roll and get a sum of 3, or a sum of 4, there are 3 ways that could happen. I could roll a 2, then a 2, but I could also roll 1, then a 3, or a 3, then a 1. And that gives me 3 ways that could happen, or 3 out of 36. Now we're starting to play craps here a little bit, because which sum is most likely, probability wise, to occur? It's 7. For 7, that has the most number of ways to obtain 7, and that the sum of 7, and that is 6 different ways. And now at the end of the day, where I was really wanting to go with this situation is, when I actually draw the graph out, the histogram, you see an exact normal curve again. It's just that bell-shaped curve. So like when there's only one way to get a sum of 12, and there's only 2 ways to get a sum of 11. There's only 3 ways to get a sum of 10. So you get that Again, normal curve. Okay. All right, so now you, especially if you follow sports and or at least bet on sports, and I'm not advising that at all, but it is a popular thing to do. You will hear the terms probability, and you will also hear the terms odd, the odds, right? Or what are the odds something happens? And we tend to kind of think of those as synonymous, but really they're not. Um, Two different meanings. So odds are commonly stated as the ratio, which means fraction, um, of the probability that a certain particular event will occur to the probability that it will not occur. So if I say the odds for an event A are given by probability of A, what is the probability of that event, divided by the probability of not A. The odds against an event A are given by, and it's just reversed, probability of, so up in the numerator, if you're calculating the odds of something not occurring, then the probability that it doesn't occur over the probability that it occurs. Now, generally in gambling, and just because I study probability, I'm not much of a gambler. Oh, almost always lose. But in gambling, it is odds against. When you hear odds, it's almost always the odds against something occurring. So, so as an example here, talking about, if I were to look at what are the odds of getting two heads when tossing two coins together, what are the odds against it? Right? So what are the odds of getting two heads tossing two coins together? Right. So now, so the odds for getting two heads together. Now remember that means for the probability for an event occurring, the probability of A divided by the probability of not A. Right. So the probability of getting two heads when tossing a coin, that's got to be 1/4. That's this. That was 1 out of 4 possibilities when throwing two coins. Now, probability of Then by not getting 2 coins, that was 3/4. There were 3 ways that could occur. And now, so remember with complex fractions, flip this, multiply. So it's 1/4 times 4/3. The 4's cancel. So I get what? 1/3. So what is your odds of getting 2 heads when tossing 2 coins together? It's 1/3. You got a 1/3 chance. That's your odds. Now, this was going to, again, if you follow sports and, what is the betting line of a team, winning the Super Bowl or something? It's almost always the odds against. So notice this is just a flip of this one. So what are the odds of not getting 2 heads in this situation? Well, it's a flip of this. So that's going to be 3/4 over 1/4, which will equal, at the end of the day, we could say 3/1. And so you would say, what are the odds of not getting 2 heads? 3-1. Your odds are 3-1. All right. Let's see. All right, do one more problem, and we'll call it a night. All right, so we're going to go to a horse race. So we're at some horse track, we're at a horse race, and the odds on a horse named Blue Moon are given to be 7-2. So horse race. The odds on Blue Moon are 7-2. Okay. So let's say you bet $10. And Blue Moon wins. All right. How much will you gain? Given those odds, right? So what does this mean? 7-2. So for each $2 you bet, you gain $7. Right. So a $10 bet's equivalent to 5 $2 bets. So at the end of, so for each $2, you gain 7. Then you could say that's going to be 5, because again, if you bet $10, that's like 5 $2 bets. So you would be looking at 5 times your $7, which is going to give you $35. Plus you get back your $10 that you bet to start with. So that's, at the end of the day, you're going to gain that's what you're going to gain, but what you're actually going to get paid back when you go collect is $45 when you go collect them, but you would have gained 35. All right. So then, one last homework assignment, and it's going to be 7A. Now, as of right now, it's the homework as I have it in here right now. Let me go ahead.